Morning session. As usual, there are a couple of announcements before we get started. End of week reminders, I won't bother reading for you. And Steve asked me to tell you that the videos from the talks from Tuesday are already up on the website if you want to check them out. And the other ones will be up soon. And we would welcome any feedback that you have, either in person or by email on the website.
Can we say thanks to Steve for?
Yeah, I think that's great. He's done a great job. Okay, our first speaker this morning is David Wilson from Microsoft, and we'll speak about art shuffling and Diophantine approximation.
And this is joint work with Omer Angel and Val Perez. Okay, so we're going to talk about what's called the overlapping cycle shuffle. So if you have a deck of n cards, you flip a coin to decide whether you're going to pick the bottommost card, the nth card, and put it on top of the deck, or else you're going to take the n minus kth card, say it's this one, and move it to the top of the deck. Okay, so if we write these two permutations in cycle notation, the first one, when we take the bottom card and move it to the top, is this cycle of length n, and the other one is this other shorter cycle of length n minus k. And this is in part why we call it the overlapping cycles shuffle. Yes?
Excuse me, is k some fixed number here?
For a given shuffle, it's fixed.
Yes. And it's overlapping because these two long cycles overlap in n minus k over.
Right. Okay, so this is the special case when k equals 1. You either take the bottom card or the n minus first, which is the second from bottom card, and move it to the top. This is also called the Rivella shuffle.
Yeah.
All right, so Hildebrandt showed that this takes order n cubed log n time to mix, and Diaconis and Self-Cost also showed this using a different method. And later I showed that it actually does take order n cubed log n time to mix. So Goll and Unison looked at a generalization where instead of taking one of the bottom two cards, moving it to the top, you take a uniform card from the k from the bottom and move it to the top. And they show that this takes order n cubed over k squared log n time to mix. And the other generalization was looked at by Unison, where you take either the bottom or the one, or the n minus kth. And he showed that it takes at least order n cubed over k squared log n time to mix, but there wasn't any kind of matching upper bound, and indeed there can't be, because he showed that if you take either the bottom card or the n over 2th card and move it to the top, that this is going to take at least order n squared time to shuffle. And for any fixed rational, if k is equal to that rational times n, then it's going to take order n squared time to mix. But he conjectured that for typical values of k, that it would take order n log n time, just like this other shuffle would for typical values of k.
For the top result, is that for fixed k? I mean, k not growing with n? Or?
K is allowed to grow with n. Although,
I mean, like if k is n over 2, that seems to disagree with the. Oh, those are two different. Oh, sorry, those are two different.
Two different shuffles, yeah. Okay, so we were interested in how long it takes. So unfortunately, looking at the mixing time of the whole deck of cards is hard, and that's still an open problem. And so we looked at the somewhat simpler problem of just looking at a single card and looking at how long it takes to mix. And experience suggests that the whole deck would take about within the factor of log n more. Okay, so this is the relaxation time of a single card as a function of n and k. So n is the size of the deck. It ranges from 1 up to 200. K also ranges from 1 to 200. K is at most n, so that's why this plot's only defined for this triangular shaped region. And as you can see, the relaxation time, which is the reciprocal of the spectral gap for a single card, is this complicated function of n and k. So this is the Markov chain for a single card. If you're within the top n minus k, you always deterministically go down one level. If you're at the n minus kth, you either go to the top or you go down one level. And if you're below the n minus kth, you either stay where you are or you go down one level. So if you run this Markov chain for a long time, the position is going to be approximately uniform. And so the number of times that you're at position n minus k is going to be more or less about t over n. And the number of times that you're greater than position n minus k is going to be about t times k over n. And so just at a heuristic level, to try to understand why we have this complicated behavior, the position at time t minus t is approximately negative n minus k. This is the number of times that we're at position n minus k, and of those times, about half the time we go to the top and we subtract off n minus k. And this is about the number of times that we're near the bottom of the deck. And when we are, we have a 1/2 chance of staying where we are, so that's why we subtract that off. So the binomial is approximately a normal random variable. And okay, so we can approximate the position at time t by some deterministic function of t, k, and n, which we really don't care about since it doesn't affect how close the card is to the uniform distribution. Plus, well, okay, so negative n minus k times this normal. Since we're taking it mod n, the n, it doesn't matter. So it's k times the floor of this normal plus this other normal modulo n. All right, so the picture here is that the first normal times k gives us centers about which we place other normals. And then we take this mod n. Okay, so these are distance k apart. The typical number of states there is going to be square root of tk over 4n, and the typical number of centers here is going to be square root of t over 4n, And so most of the mass of this distribution is supported on T root K over N states. Okay, so that implies when K is of order N that you can't have mixed in less than order N to the 3/2 time. And that's for any value of K which is of order N. But if you have K, say K is N over 2, then all these centers, when you take it mod N, they all line up. And so there's a much smaller set of values modulo N that this distribution is largely supported on. And in that case, it takes order N squared time. So at a heuristic level, that's what's going on. Okay, so these plots are showing what happens for a large fixed value of n. N equals 200 on the left. This is the reciprocal of the spectral gap as a function of k. And okay, so you can see the bumps at simple rational numbers. Okay, so we show that if you're focusing on the rational p over q, which is in those terms, that the height of that bump is pi squared pq over, well, okay, so the height is the reciprocal of this thing, which is, okay, so that would be 2n squared over pi squared pq, and then there's this funny factor of either 1 or 4, depending on whether or not p and q are congruent, mod 2. And okay, so the reciprocal of this function is plotted. Those are the spikes, and you can see that there's pretty good agreement with the relaxation time.
That's not a very continuous function.
Which is it?
This thing at the bottom, your curve is nice and continuous, but your
Actually, well, the curve, yeah, it does more or less look continuous, but it is discrete. And you can tell this even in this picture if you look on the left, since this was done for n equals 1,000. But, all right, yes. You're right, so this isn't very continuous. Okay, so so we're also interested in what happens if n is large and k can take on arbitrary values, not necessarily simple rational times n. And we show that for any k, the spectral gap is at most constant times n to the minus 3/2, and it's at least a different constant times n to the minus 3. And those exponents are tight. And that for most values of k is of order n to the minus 3/2. Okay, so the other thing that we looked at is how wide these bells are that are centered at the spikes. And each of them is of width order n to the 3/4, except for the one on the left, which is of order n to the 2/3. So for any fixed rational, if you look at the width of this, it's order n to the 3/4. But as you can see, if you change which rational you're looking at, the widths become smaller, and so there's a prefactor which depends on p and q times the n to the 3/4. Okay, so this is what the theorem is. So in addition to giving the width of these bells, we also determine their shapes. And this is the bell centered at 1/3. Agrees pretty well. And this is the set of all bells centered at all the rationals. And so the next theorem we showed is that if you take the supremum over all these bells, that this is asymptotically equal to what the spectral gap is. And you almost can't tell that the spectral gap is plotted, except that occasionally you see these little enlargements in the curve there. And that's the actual value for n equals 1,000.
The big spike on the left, is that what you get just by summing all the standard shaped bells as you go to 0, or is there some other effect there?
No, the bells aren't summed. These are the, we're looking at the maximum bell. The one at 0 is a little bit different in that the height is n cubed rather than n squared, and the width is order n to the 2/3 rather than n to the 3/4. But
Some arbitrary reason.
well, no, it's not completely arbitrary. Okay, so I'm not going to prove these here, but I just wanted to indicate how you might go about deriving what the spectral gap is, and perhaps explain why the bell at 0 is a little bit different. I guess one other comment I would have is that if you that the values for arbitrary k, typical values of k, where you get n to the minus 3/2, is a consequence of this formula where you take the maximum over all bells. It's just that for a typical value of k, you would look at what the nearby rationals are, see how high the bells are, and if you work it out, you end up with this n to the minus 3/2. Okay, so recall that this is our Markov chain at the top, and it's sufficiently sparse that we can compute the characteristic polynomial of the transition matrix without too much effort. And this is the characteristic polynomial, and if we set it equal to 0 and rearrange things a little bit, we find that the eigenvalues have to satisfy this equation, and this appears in Jonassen's work. Okay, so if you actually plot these eigenvalues for a given value of n and k, this is what you get. You end up with 2 overlapping cycles, which is the other reason that we called it this. Okay, so this outer cycle is centered at 0 and has modulus very close to 1. The inner cycle has radius 1/2 and is centered at 1/2.
It also has modulus. That's very close to a circle as well, isn't it?
Yes. Okay, so let's see if we can at least understand why the eigenvalues are distributed like this.
David,
Yeah?
do the dots actually overlap?
Do the dots overlap?
As circles, they overlap.
As circles, they overlap, yes.
Are there any multiple roots?
There are no multiple roots. Okay. All right, so suppose that we have some fixed constant like 0.99, and suppose that the modulus of lambda is less than this fixed constant, which is 0.99. then lambda to the n minus k, well, as long as k isn't very close to n, which is perhaps some indication why the bell at n equals 0 would be a little bit different, then lambda to the n minus k is going to be exponentially close to 0. And so then if we solve that equation, substituting lambda to the n minus k is equal to 0, we find that lambda is approximately a kth root of minus 1 over 2 plus a half, which explains the inner cycle. Okay, so the other case that we have to, well, okay, so lambda is an eigenvalue of a transition matrix, and so we don't have to worry about the modulus being bigger than 1. But the other case that we have to look at is the modulus being approximately equal to 1. And we're going to assume for the moment that lambda itself, not its modulus, is far from 1. Or I should say not very close to 1. Okay, so all right, let me draw a picture here. Okay, so this is 2 lambda. It's a circle of radius 2. And if we subtract 1, we move the center here. And every point on this outer circle has modulus bigger than 1, except for the points that are very close to 1. Okay? So this 2 lambda minus 1 to the minus k is going to be exponentially close to 0 as long as lambda is sufficiently far from 1. And so if we substitute that into the equation, we see that lambda is approximately n 1 over, well, it's the n minus kth root of a half. Okay, so that explains why these eigenvalues are more or less evenly distributed. The 1/2 to the n minus k is essentially 1. But the other thing to notice is that for these eigenvalues, the modulus is about 1 minus order 1 over n. And that's because of this factor of a half there. Okay, so if we're looking for eigenvalues for which would have modulus which is much less than order 1 over n, that narrows the search down to this region where lambda is about equal to 1.
Modulus, the difference of the modulus from 1.
What?
Eigenvalues where the modulus is close to 1.
Yes. Much closer than distance order 1 over n. And in the end, we see that there are such eigenvalues. Okay, so just one other comment. So these eigenvalues are more or less evenly spaced. These are about evenly spaced. And when they're very close to 1, it turns out that they're also about evenly spaced. And so these eigenvalues kind of struggle a little bit to intermesh where the two cycles overlap. Okay, so if we focus our attention on eigenvalues that are close to 1, we can think about doing series expansions. Let lambda equal e to the minus epsilon plus I pi a. And similar expansion for lambda to the n minus k. All right, so the first thing you can show is that for epsilon, much smaller than 1 over n, a is small, so that's more or less what we showed on the previous slide. And you can also show that b is small. And given those bounds, it becomes easier to look at the series expansions. You get an improved estimate on precisely how small a and b are. And then using these new and improved estimates for a and b, you can go even further with the series expansion. And do some calculations, and you end up with this formula. That lambda has to satisfy this equation for some integer m, and I'm not going to go through the calculations. And the next thing is that if you have an m which is small enough, and this term is small enough, then there is an eigenvalue of that form. And you can think of doing that by just taking lambda and substituting it into this equation and doing something like Newton's method to repeatedly refine lambda. And it zeroes in into a 0. Okay, so if we want to find the spectral gap, what we want to do is maximize this estimate for the eigenvalue. And this is more or less the same as minimizing this expression, where this norm here is the distance of a given number from the integer lattice. Okay, so there are a couple of differences here. So first of all, there are other eigenvalues which aren't of this form, but those don't matter because for those eigenvalues, the modulus is sufficiently small that they aren't going to be the ones that give the spectral gap. And in this expression, there are terms for which m isn't little o n over k to the 1/2, but those don't matter because when m is that large, this term makes the expression sufficiently large so that you can show that that's not where the minimum is achieved. And there's some special argument to show that you don't have to worry about m equal to 0. And anyway, so in the end we get this expression for the spectral gap. And m more or less corresponds to the denominator of the rational at which the bell is centered. And when we take this modulus here, you're subtracting off an integer. And that integer that you subtract off more or less corresponds to the numerator of the rational at which the bell is centered. Okay, so I'll stop here. If you want to read more details, it's on the web.
Any questions?
Yeah?
What would you expect if you chose two different offsets? That you choose the bottom card or two other, or even forget the bottom card and just want to consider two different, well, I guess, yeah, here, but I have to, yeah, okay.
Okay, well, so if we go back to this heuristic understanding of what's going on, we would have not these two different Gaussians, we would have three of them. So, okay, so in that case, we'd have this large one with the gaps equal to the first offset, and about each of these, we'd have a distribution of centers where the gaps between them would be given by the other offset, and then about each of those, there would be a more or less continuous Gaussian. And based on that, you could figure out about how large these Gaussians would have to be to hit enough states. And so that's what I would expect would happen. So the more precise estimates I can't really tell you right now.
Hey, thanks again.